Greetings, everyone. My name is Harshit Agarwal, and this is my project as a part of IoT and Edge Computing course under Professor Chandra Maulishwaran Shankaran sir. My project is live weather classification, wherein I'll be training a neural network and then running the inference model on a microcontroller, namely the ESP32 board. Over here, I have my Python notebook file, and first I'll be defining a few modules. After that, I'll be reading my dataset. The dataset in question over here is this one. It's a weather dataset which has few parameters. The first one is date. Date parameter is of no relevance to this project as we are not working on time series images. And then we have precipitation, the maximum temperature, minimum temperature, and wind speed. All of these four parameters will be considered for training the model. And then we have the label set, which is the weather. And I have five different classes over here, that is drizzle, rain, sun, snow, and fog. After reading the dataset, we notice that while doing info of it, we find that the data type of all of them are object. This won't be ideal for training the model, and hence we typecast them back to float. After that, I plot a pie chart of it to visualize the different distribution of all the labels. After that, I'm trying to hot encode the labels. That is, for a particular label, if it belongs to that particular class, it's going to represent true. Otherwise, it's going to represent false or zero for all of it. That way, we can pass this on to a neural network and it can work on it efficiently. After that, I am extracting all the information. That is, I am omitting the date and I'm extracting all the relevant parameters for the X training parameters and then labels. Similarly, I'm taking the hot encoding labels of it. After that, I'm splitting them into testing and training. I have 20% for test size, another 80% for training set, and then random set of 42. After that, let's define our neural network over here. The input layer will be of 4, that is because there is 4 parameters, and the first layer will be of size 32. I'll be using the activation function relu, and the final output layer will be having 5 different classes, and as it is a multi-class classification, we'll be using softmax function. The data is of the continuous type, so we'll be using mean square error and optimizer Adam and metrics accuracy. Over here, I'm printing the summary of the model. After that, I'm training the model for 100 epochs and batch size of 80. After running the model for 100 epochs, we get an accuracy of 83.2%. After that, I'm just predicting the model for a random set of input, and we can see it is working properly. After that, I'm trying to export the model by first converting it into a TFLite model. We require TFLite model because the ESP32 board cannot handle large and big complex models. So we have to convert it down to a lighter model. For this, we'll be using TFLite. So first, I'll be reading all the weights from the Keras model. After that, I'll be using optimization. I'll be setting the parameters and passing a representative data set. This will be formatting it for a type, and then we can use that type to read from the header file. After that, converting the model, we're saving the model in this particular whole file called weather regression model.tf which is this particular file. After exporting the weights, the TFLite, we can now verify that if the exported weights are proper or not. So for that, we'll be using this TFLite interpreter. We'll be reading the model and trying to compare it to the original model which we trained. So over here, I'll be having a few random set of inputs, namely 3 different sets. And I'll be running them for both the TFLite model, the interpreter, and for the real model which we just trained, the original model. So you can see after running them, this particular one is for the TFLite, this one, and this one is given by the the real Keras model. You can see they both are pretty similar and accurate. So we can say that, and we can also observe that This particular TFL model is giving more rounded up version because it is more less complex and it is more lighter. As for the original model, it's more complex and it's giving more precise values, e power minus 14, which is a very small number. So now that we have verified the model works, we're exporting all of the weights into a C header file, which is given over here. It has all the weights from hexadecimal. It is all the required parameters, the dense size and length. And then we have the ESP32 code over here. We'll be getting the data from API calls. And to get API calls, we need to have internet access. Luckily, we have ESP32 board which provides Wi-Fi access. So for that, we'll be needing Wi-Fi module, an HTTP client module for getting the data and authorization, and then we have Arduino JSON because the data received fetched from the API calls will be of format JSON. So I'll be using Arduino JSON to pass them and deserialize them into extracting the relevant information. And then we have eloquent tinyml. This will be the inference model engine running the weights which we have passed to it. And then I'm including the header file itself. Over here, I have my password and the SSID of my hotspot. The board will be using these particular credentials to connect to the internet. Over here are my credentials for the API call itself. I'll be demonstrating this in a while. Over here, I have two APIs. The first API is for getting the current date. So I'll call this API once to demonstrate. So yeah, this particular API call is gonna get the current date. Now we can see, we can get a formatted today's date 2024 of November 16th. So we'll be using this particular thing to append to this particular API call. This API call is of this format. We have a suffix, we have a prefix over here, the Meteor Matrix. Meteor Matrix is the platform cloud provided us which gives weather information. We'll be using this API. I've set up a free trial over here. So it is of this format. We have a prefix over here. I'll be demonstrating this also. And then we have the date. I'll be copying today's date. This date will be fetched using the previous API which I just shown. And then we have the suffix. The suffix has a few parameters, that is precipitation, temperature maximum, temperature minimum, wind speed. That is, I want these four parameters to be fetched from the API call. And also, I'm passing the latitude and longitude from where I want the data to be of. That is, I pass the latitude 12.97 north and 77.59 east, which is the latitude and longitude of Bangalore. That is, I want the Bangalore's parameters for these four types. I'm copying this and also mention I want JSON type to be fetched. So after calling this, you can see it's asking for credentials. These credentials are provided by this HTTP username and password. So if I'll paste this over here, sign in, and it's going to give me the required parameters and information. And then I have defined two task handles. One is for fetching task handle and one is for inferencing task handle. Fetch is going to retrieve the data from the API calls, and inference is going to inference the model, inference the data, and try to print the result over here. And then the data communication between the two cores. Fetch model is the fetch task is going to be running on core 1, and the inference task is going to be running on core 0. It will be running parallelly on two different cores to maximize efficiency. The communication between these two cores, the data transfer will be done using a message queue. That's why I defined a queue handle over here. I'm defining a few stack queue size over here with some size of stack size of each task. Then I'm defining the parameter structure over here. This will be holding the parameter values, which has all the four parameters required. And then I'm defining temp data object, the structure object, which is going to be holding the current values received. And now I have generated pool. Basically over here, I have an array of structures and each value is a random set of data. This is because just in case if the Wi-Fi is down or there is no API access or the API call is been exhausted, that time it's going to call this function and it's going to send a random set of value from the generated pool to the inference engine so that the model doesn't stop. Over here, I have defined the number of inputs and number of outputs for the model and the tensor inner size. Tell me how much area should tensors be allocated for. And then over here, the eloquent tiny ML object itself, it's going to take all the parameters and it's going to start the TFLite model. Over here, I define all the classes. That means I can take the most highest probable value, the highest probable index. I'm going to print the particular corresponding value. Like I consider I have the second index as the highest one. It's going to print the fog value based on this array. So initially I created a queue, which I said the limit of number of items 10 and size of x value, that is parameters. Then I created a first task over here for data fetcher, which will be running on core 1. And this is the function data fetcher function, which will be there defined over here. And we also have another task running on the second core, that is the core 0 for inferencing, which will be running inference task function. And over here, for all the pool size, I'm generating a random range of value from the probable ranges and then setting them up. ML.begin is going to start the model. It's going to take the parameter weather model ESP, which is given over here. After that, I'll be running, starting the Wi-Fi begin. I'll be trying to connect to the Wi-Fi. And if it is no connection, I'll send a random input by calling this generated input function. If it is connected, it's going to print the credentials and going to start getting the values. So this function takes generated pool, copy to temp data and send it to the queue, which will be read by the inference task and print it. But if there is internet access, we'll be using data fetcher. First, I'll be defining dynamic JSON document. This be deserialized JSON files. After that, I'm setting a time interval, like how much in how much time it should inference every few time intervals. So initially, I'll be using the first API call to get the current date. That is this particular API to get the current date. This particular API to get the current date. After getting that, I'll be deserializing them and get the payload, the particular required format, that is the date required. If just in case there is an error, it's going to call the function generated input and going to pass a random set of values. We got the correct proper date. It's going to again call the API. Before that, it's going to make a server path. That is the first prefix, the current date, and the suffix. It's going to combine them to a single string and call it to the HTTP. It's also going to authorize it and get the required values. Again, after getting the data, it's going to try to deserialize and pass the outputs. If at any point there is any error, it's going to call the generated input function and pass a random value. If all went well and we got the data, it's going to pass it to the queue, and the queue data can be read by the inference engine. Inference engine is this one. It's running this. It's going to receive values from the queue. It's going to wait for 2 seconds before it retries and predicts the value. After predicting the value, after getting the probability distribution, it's going to call a function which is display output. So it's going to go to this function. It's going to go through all of them and find the maximum value out of all the 5 probabilities and set the index of it. That means if we assume we got the third index as the maximum one, it's going to set that index, and using the array which I mentioned earlier, it's going to call that and print the value. After that, we have getting the inputs, and it's going to keep on going that in loops. Now I'll be running the model to show a demo of it. Before that, I'll be turning on my hotspot and plug in my board. you can see over here, it's connecting first. It's showing no Wi-Fi, but then yeah, connected to Wi-Fi. And then we got a HTTP code over here. We got a response. That means we got some data. We can see over here we got precipitation. Uh, we can see over here. One second. We can see over here. It first got a HTTP response for 200. That means data was fetched successfully. And it's we can see the parameters which received over here. The precipitation, coordinates, temperature, all of it is received over here. So extracting it and sent to the inference engine. And the inference engine predicts it's raining.
Which, seeing outside and considering the Bangalore temperature, I can safely say, yes, it is raining. Now, I'll turn off my hotspot and check once again. In the meanwhile, we can see that the predicted outcome weather showing fog is usually given out when a random set of data is sent. That means there is no internet and it's in the random pool. Now, I'll disconnect my Wi-Fi and now check again. So you can see over here, no Wi-Fi connection, sending random input, and then it's going inference fog. And that's about it. Thank you.